Okay, a few more examples before I'm going to turn you loose on the worksheets for this, because you definitely want to get some practice doing this on your own. Those last two examples are called Aldol reactions, or sometimes Aldol additions, because we're essentially adding two molecules together. And they don't lose any atoms when they do that. They're really just rearranging. If you look at those two ethanol molecules, when they come together, the resulting product still has all of the atoms that were present to begin with. They're just connected in two molecules. Well, an aldol reaction, an aldol addition, can turn into what's called an aldol condensation. That's kind of a follow-up reaction. Sometimes it happens automatically. Sometimes we can make it happen by heating up the aldol product that we get to begin with. And so here is the first product we made from that last page, the 3-hydroxy butanol there. This little triangle is the symbol for heat, meaning we just heat the container that we've done the reaction with, and it does a dehydration. You can see we lose the OH group, and we're losing one of these two hydrogens that's next door to it. And so this is referred to as an alpha-beta unsaturated compound there. And so now we've created something that, well, we already knew we can do with alcohols, which is to dehydrate them. This time, though, it's happening in concert with a aldol type of reaction. So we get what's 2-butenal, the 2 telling me that the double bond with the carbons starts at carbon number 2, and as it says, you get cis and trans isomers out of this. We won't worry so much about the relative amounts of cis and trans, but just the fact that we can get an alkene to form from a corresponding aldol reaction, which just shows kind of the versatility of these types of reactions. All right. Now down below, as it shows here, ketones can do the same thing. Ketones also have alpha hydrogens. Typically they're not as reactive as aldehydes, but they can still do that. And so here's the simplest ketone, propanone or acetone here. I guess we can call it by its official formal name. And so we're going to couple together 2 propanones here. One of those molecules forms its enolate, and I've shown it here up top. And then again, once it's formed, as soon as it's formed, those electrons are going to come down, find this carbonyl over here, and take 2 of those electrons and put them up top, and then again there will eventually be a hydrogen that comes in that will make a bond to that oxygen there. So this is the initial product we get. Looks a lot like what we've just seen, with the exception that we are using a ketone instead of an aldehyde. And so you can see this long name results. We still kind of favor the location of the carbonyl group, so this is named as a ketone, a pentanone, and it's also got that hydroxy group. We still call this an aldol reaction, even though technically we haven't used any aldehydes to do this. We're just using propanone, but it's a very similar type of situation. And again, it's possible to sometimes isolate this first product, or with a little application of heat, we can also cause this to dehydrate. And just like the above example, notice that carbon-carbon double bond forms between the alpha and beta carbons. This one, by the way, would be the gamma carbon, but we don't get a double bond there. There's some stability to be realized if you have a double bond, single bond, double bond combination. We say that these bonds here, these multiple bonds, are conjugated, so they get some stability by doing that, and so that location of that double bond is always to be pretty close by to that carbonyl carbon, and it'll specifically be that alpha beta unsaturated molecule like you see here. Okay, last example down here. You don't have to use 2 identical molecules that are coupling together. If you only have one ketone or one aldehyde available, then it has no choice but to couple with itself. But we can make what we call mixed aldol condensation reactions by adding, well, 2 different carbonyl groups. And this works nicely, as it says, if we only have one of them that's capable of forming an enolate. And this simple aldehyde here, formaldehyde, it does not have any alpha hydrogens. Both of its hydrogens are directly on the carbonyl, so those don't get removed. If we mix that with some ethanol here next door to it, well, we've just seen in the first example, we can take one of those alpha hydrogens off. We can make this enolate up top here. And so this enolate can do its magic. It certainly can react with a fellow ethanol, but now it can react also with this formaldehyde. And so we can get what we call a mixed aldol product. Initially 3-hydroxypropanol, but again, if we remove that OH and one of these hydrogens, we can put a double bond there. We once again get our alpha beta unsaturated molecule there, and we can name that as propenal. Propene because of the double bond between the carbons, and it is an aldehyde as well. Okay, so when we do mixtures like this, we try to avoid having two molecules that can each form their own enolates, because then you just get complicated mixtures. I mean, in this case, we do have to put up with the fact that some of the enolate that we initially make may choose to react with some neutral ethanol. Although if we've got formaldehyde floating around, it's especially reactive for having enolates attack it. So the product mixtures are a little bit easier to separate out. But the worksheet that goes along with this gives you some examples of enolates that you can create and then couple to form the corresponding aldol products. So it's going to be good to get some experience doing that kind of thing.